This is generative dance music. Oh. All right, we're live streaming. Everywhere. Where did you just come from?
Oh,
You just come straight from town.
no, I'm seeing it from 2 days already.
Yeah?
Yeah, a little bit earlier.
Yeah, me too. Yeah, it's Wednesday. Yeah. Getting acclimatized.
Yeah. I wake up at like 2 in the morning.
Oh yeah, well I did my jet lag. My casing, it's part of the cruise travel. It's fun. Oh, wait.
Yeah, not so bad. 9 hours.
That is good. Yeah. It's your
And 7 hour break.
that time a bit closer. Oh no, I guess you go closer. Yeah. You don't get on a plane
Yeah, that's the downside. I wanted to come to the music co-creation and co-creation stuff with John Heller.
Oh, you torn between. I mean, I had to be at this one, but they all did it. Social justice one.
Oh, yeah.
Is that just tomorrow? So,
I think it's just tomorrow.
Yeah, we've still got the morning.
And, yeah, it's in parallel to the music one.
Well, we were almost going to chop this down to just a day. But
That's right.
yeah.
I wanted to come tomorrow for the music one. So.
Well, no, it is. Yeah, it is on tomorrow. there's not actually presentations. Maybe there's a couple of paper presentations, but it's mostly actually more like Michael's actually going to be presenting. They've run a prize for generative music systems. Yeah, so it's not actually paper presentations tomorrow. It's that, and then panel discussion. Are you going to come to the concert tonight?
Yeah.
Yeah. So there's a panel discussion with the musicians, with the artists. So it's actually a chance just to understand what they're doing. And then there'll be a bit more of a community discussion about which direction we work each other with.
Yeah, Wednesday on the panel for 1.5 hours.
Yeah. Well, that's right. You don't have to speak for 1.5 hours.
No.
5 people, I think.
I don't know.
4 or 5 people. 5 people. So 1.5 hours is not very long time if everyone's going to talk to it.
Yeah, we just put emphasis on paper on the
in the main conference, right?
Yeah.
Yeah. Yeah, good. Okay. It looks entirely different from what I saw. That was 3 weeks ago.
I know.
You guys work fast? Or is it just a reskin?
Yeah. It's like, oh, you'll see.
Just click a button.
We now have
Choose a different skin.
we have music tracks. So when you can buy quick sign,
Oh, really? After that conversation? My advice was don't bother.
Yeah. You could. We now have how many the track mixer of 8 tracks, no, 6 music tracks, 5 ambient tracks, different audio sounds in volume, and then the programmer guy had to redo the entire audio.
That's actually very interesting because there is a while ago Native Instruments, that company that make hardware and software. They put out this kind of file format. Really stupid name is called stems. But stems is actually the word to describe tracks in a and it's like a 4 times 2 channel format. So and the idea is that all of the artists would produce all of their music with everything separated into drums, bass line. Yeah.
It's way easier than
Well, it's just, I think it was just an effort to get, because one of the huge blocks at the moment is that people put out their music in stereo.
Yeah.
You download their music, you listen to their music.
Yeah, you can't
how's
separate
that ever going to transition to a situation where we have more creativity? And that was their effort, but it maybe wasn't the most carefully conceived effort. Because a lot of people are supposed to be like, well, nobody's having my company isolated. No way.
Yeah, people go in and say, oh, yeah, those drums are really good at them.
Yeah, or like, I put a load of work into the arrangement of my tracks while I want to do
the arrangement
parts.
Yeah.
So, still not, I don't think that, I don't know. You know how that works out, that schedule thing?
I think people know that.
Yeah. But of course, from the point of view of what you're trying to do,
well, I think it would be perfect.
From the point of view of someone programming and actually wanting to music out, ideal to have that ready-made engine player with a format of that.
Yeah.
It's all about the motivation. What you're saying is for.
Yeah. Well, there you go. You've got sound in that now. It's going to increase your user base by 2 people.
Hopefully, too. If it's not 2, then just like it already increased. No, it maintains the user base of 1.
Right.
What's the name of the one?
It's the app is called Profile. Yeah. Somebody, it's basically generated. Everything is on the mobile device. It's designed for iPod and iPhones. And you can design another game just using with other people. Modify the content size of notification, sharing, it's like millions of people will love it. It's like a sales. Yeah, if I build it there, yeah. But there's a couple of really interesting things. Yeah. Yeah. The original one was horrible. This one is way better. So there's like 3 Fs or something like that. And I concentrate on one, which is like less than 2.
Yeah. Right, I think we're here. I guess I'll hang back here. See you later.
Is there a program?
It's online. Go to musical metacreation.org. And there's a link on the next work.
They don't move. Yeah. Well, checked in. So yeah, transfer in the chat. Oh, yeah. Yeah, and he had like, all these irreplaceable guitar pedals and yeah, someone made it. Changed the locks, got a lockbox in there. Yeah, pretty neat. But it's totally unique. It's never happened. Irreplaceable guitar. Yeah, 8 or 9 months ago. We have a changed locks, so the revenue came all some irreplaceable. And upgrade. Also, we had a weird experience where the Android replaces all the parts and still the same.
Okay, let's get started. Welcome everyone. Welcome to our talk. So that's the beginning of the 5th International Workshop for Musical Integration. I guess most of you are going to be I will introduce and provide a quick intro and we get started with the program of today. I'm trying to speak up, but if you cannot hear me, then you might just say so, and then I'll speak even louder. And the issue with the microphone today should be resolved in 2 minutes. Musical Metacreation is a workshop that brings together all the practice and research on which creative behavior and researchers and artists are looking at those descriptive and prescriptive models of musical creativity. It does relate, and that's why we are collecting the International Conference on Computational Creativity. It does relate to the domain of computational creativity in the science of looking at AI systems applied to creative tasks for which there's no notion of opportunity very well defined, so whether it's choreography, poetry, humor, or music, we are, however, slightly different, and the physical integration as an area, if you try to define it, is definitely an interdisciplinary one that brings together both the people from the music side and the social science and humanity, as well as people that are more on the technical side, developing systems that usually are generated in nature. And there is definitely a diversity within the music community that spans from purely artistic projects that have a strong aesthetic signature, like music systems, for example, and then therefore embrace the domain of generative art, up to, on the other side, purely scientific studies of computational creativity applied to music. And then I like to think of metacreation as a domain that embraces this entire spectrum. And so we see that during this workshop today and tomorrow morning, there's a vast variety of problems that are being addressed, or creating class musical cases that are addressed by the community in this area. And there's likewise a vast variety of systems, from very specific ones to a generic one, but also from very reactive systems that have very little autonomy that still qualify to be new systems to very generative systems and very sophisticated ones. A lot of systems are interactive, some are not, and then some systems are in real time, and we see some of these at work tonight in the concert, and some are working offline. Some are machine learning systems that learn to execute music, some are more produced from scratch by their object. Wide variety of systems are there, and there's as well a wide variety to evaluate those systems, both informal evaluation as it exists for every system and or musician and computer in the real world, where the modulating cell, the user system or expressing domain, journalism, physics, agents, to decide if the system is worthy or not. And on the more formal side, there's also academic and scientific evaluations of those systems through both peer reviewing, as we do with this workshop, the papers today, as we do with program 50 that we'll do in a second, as well as some more formal studies. So the program for today, which is available on our website, Metacreation.net, is pretty dense. We have 4 different sessions. There will be 2 breaks with coffee being served, one at 10 a.m. and one at 3:50. And there's a long lunch break in the middle of the day. And then we have tomorrow morning as well with a session, presentation by Michael right here about some of the results of the academic feasibility regarding the performance of competition, which is a new benchmark and opportunity. Then we have 25 minutes where we use the rules in a bit more and more complex, where people that are able to they can open the computer, we can look at that system in more detail, ask questions and flag. We have the coffee break, we can push through that, and then after the break tomorrow, we have a community, a panel discussion where the proposers and the developers of the system that will be shown at the concert tonight will be discussed a little bit, and then there will be a possibility of an interaction between people who attended the concert, of you guys, and the proposers and developers that presented the concert tonight. I want to thank the program committee. We have a great program committee this year, very international, and with a lot of very well-known names of a lot of people that have been pioneering this very domain. And just actually make a little bit of an announcement about the concert. The doors are 7 p.m. and the concert will start at 8 p.m. It's at the Markov gallery, which looks like this, and you will stand in front of it. And it starts, and then there will be marked the address. If you want to come to the chapter, you can do it or ask we go to MATLAB, we do optimizing, and we use that to search, to find us, search on the internet, on YouTube, search a meaningful integration workshop, and then we can find this page here where we are like, but we can hear and see the light and sound of the frequency. So we can get the search the workshop of Python.
And I should mention that the microphone, I think it's just coming from the camera microphone at the moment. So people at the back whispering to each other, this is a really terrible talk. bear in mind what's the consequences of that. And people who are presenting, just make sure you. That's just a different.
That being said, the first user is joining this morning. Set up. Sharing the first session. What is the board will be sharing the second one, and then I will be sharing the afternoon.
My name is Markov. I'm here from the and so I'm here today to talk about system and system development. So personally, I've been working on youth generation for many years, but in recent years I've been but I think I really did the second so I saw something that I could use to make more practical. So I thought that would be a better framework to work in. So we started putting things together. For those of you that are not familiar with Markov, the method is edited by the programmer in real time to create music. So you have these algorithms it's not fun. So I want to incorporate integrate EC into the process. And this has been done before. Do this, but in looking at master definition, the next layer of next layer design is really meant to use the ground line. The idea is that this will allow greater creativity of artists in very quick generation and just code and editing and which then will and so when we're talking about my name, we're using a kind of right, so sometimes it's really in general. EC is a method of machine learning based on natural evolution, whereby instead of trying to optimize one individual solution, make the population a problem, and you solve the so you're constantly working on the unit together. And basically, over here, evolution, how about each of these solve the problem, and of course, this is combined together with and this way, over series generation is one of the well, the difference with the master evolution is that you're evolving a single into very, very simple information. But then if you design the grammar, the master evolution will have information inquiry section of parameters. Basically, take the genome, apply your grammar, and then consider the functions to business maps. So basically, what we have and here you have long-term look, and then you consider the choice. And either selecting or a lot more to say about it. It's not really the purpose of what I'm looking at. If I give you a big idea of what is the grammar of this system looks like, what we have done, and as I say, this is early stages, but just kind of I developed 6 different grammars to create and I'm not going to get into here what the structure is on a basis developers have an example of sort of like you can create 4 different customers but use those kind of templates. So this one is picked the complete and snare hop. So what I've done with each grammar is basically return some pre-code followed by a Markov and then you have so the pre-code basically selects the modifier code in this case it actually Markov, but then started with the follows so that's the snare hop. Similarly, we have some sign-up rates, they're a little more interesting, again with the pre-code or the trigger or the and in this case, we see, okay, so in our scale line, we've got 4 different options there. There's a few which create scales late, so kind of look at next one. You can play around with parameters. So the real design part of this kind of design is really at the moment, in an easy situation, that is not very difficult. You change the fitness right and do the thing, and the fitness thing, no need to go into the word of but in a situation where you have you know that are full goals, all the things in valid so, I actually run a checkbook. Sorry, another part of it is basically while we're doing and then this would work just as easily as for example, just to say crash. So our mechanism is stop working and started running, and then we listen to what they do. So what I can do. That's one of the signs that so what we do, the idea is we run code in real time. What would happen is we have the macro evolution and the back end. Overwriting one thing. If you say one, you can then switch your out and say you can open up any one of them. You can change it and save it, and then run it and max it, and it's quite different. So I now have a different kind of it's going to be my error. So the new file is generated separately. Really great. So, sorry. In a nutshell, you can add in what you but the idea is that instead of capturing the file, you can generate a file and depending on what you're actually working on, that's what you can do. So, so that's the idea of it. It's a very simple thing. The grammar is very important. It's basically what I'm doing is the life coding. It's not technically life coding on unless you go to the next part. It's basically the process of the first time. So
so the idea is to like either you will do it offline, you will I will the code generated is it human readable? The code generated is human readable.
yes.
So the idea is you can do that while you prepare your set, you have things set up ahead of time, you will select the one you like, and eventually you select them like that.
Yeah. For me, it would be more like a visual game. When I sit there and I have to put that generated it's a bit of a, you know, English anyone has a broad street grammar. But what could be what is the top of the and when you're selecting and
time for a few more questions. We were on the last as well as the next presenter, the computer gets set up. And I think we have a gentleman here that is working on solving all the technical problems.
Yeah, that comes from the area of so
Even within that, you can see that it was individuals who like and have, like that's what I have it directly. These are successful and started off in a couple of those and have very success.
yeah, because that's what it's
What do you think about this? So we
everything works. Too loud. Okay. All right. Hello, everyone. Thank you for coming. I'm very excited to be here. My name is Computational. Our co-authors who are not here are my classmates, James, and Professor Scott Barton here, who you will hear from later, also here. And of course, in terms of that we're using recurrent neural networks to judge fitness in musical kinetic algorithms. A little bit about who we are. We are three of us are students at the Worcester Polytechnic Institute. Mostly as an engineering school. Of course, we are part engineers, but also part musicians, and we have kind of a joint interest in artificial intelligence and music. So a bit onto what we're doing. The overall goal is to generate monophonic improvisations to record progression automatically. There are many various social approaches to this, of course, one of which is heard about is genetic algorithms. And you've heard a good overview, so I don't feel like I need to do that again. The difference between our system and what Dr. Larkin described is that we don't have any variants, so the mapping from our genotype to our phenotype is much simpler, and I'll go over that when I get to the design. Of course, what you need when you have a genetic algorithm is a fitness function. And there are many ways to go about writing one. You could choose random for some application. You could write your own based on rules and metrics. And that works a lot of times when what you're trying to generate is very structured. But it doesn't work as well for something like improvisation, where variance and nuance play a more important role. So what else can we do? We could ask humans. After all, generally speaking, the humans know the criteria for what we're trying to generate. So if you want to know whether any individual in the population is good, you can just ask the human. But the problems with this are that it's time-consuming because you have to listen to everything in real time. It's expensive along that same lines, and as we show in our research, it's incredibly inconsistent, which is problematic for converting into like an actual good solution. So what is the final approach? In my opinion, the final approach, the ultimate approach, is to learn the fitness function of data. Technically speaking, what I mean by this is that we want the fitness of an individual to be the likelihood in some sense that whatever individual in the population represents, the probability that was drawn from some training set distribution. Right? And of course, this is what the approach taken by the various kinds of neural networks, including recurrent neural networks. Their job is to estimate that probability. So overall, we were wondering whether we can use recurrent neural networks to judge the fitness of individuals in a genetic algorithm architecture. Right, so as I said, we're trying to evaluate RNNs as a data-driven fitness function. And we're also interested in how they compare to humans. So not just can they produce music that we like or deem correct, but how do they vary in terms of consistency, speed, musical correctness, and whatever the factors are very important. All right, so to go about this, we started by building a genetic algorithm, which we essentially cloned from GenGenome, a very successful interactive genetic algorithm written by Al Wiles 2 decades ago, more now. And we chose that one just because it worked well. It has lots of good papers describing its implementation, so we're easily able to reproduce it. And it's interactive, which is of course important if we're interested in how RNNs compare. The second half of our system is of course the recurrent neural network, which we conveniently got from Google's Magenta project, which is broadly focused on generative creative works with neural networks. But one of the main things they do is architectures for recurrent neural networks. And they also provide pre-trained versions on massive label data sets, which are full advantage of research. So basically after programming GenGenome from scratch and building some Magenta RNNs into it, we were able to generate music either with human training, so that's that keyboard, saying good, bad, providing feedback to the individuals as they play, just like in the original GenGenome, or with the recurrent neural network. Okay, so I'm a big fan of giving a taste of results first, so I'm going to play 3 quick short samples for you. Okay, so this first example is when the human was providing fitness feedback. So this is essentially like a baseline ordinary interactive genetic algorithm. The piano chords are the backing track, basically the chords are kind of generated over, so those weren't generated. We just picked some chord progression, and the trumpet sound, which is what was generated on top of that. And then for comparison, we have the RNN training example. And these are both like quite good examples. But not perfect. And as for full disclosure, I have a significantly less impressive example In this instance, we also set 16 minutes as the smallest duration you can play. And technical advantage of that. All right, so I hope that sets some applications, gives you an understanding of what we're trying to do here, the scope of this project. And so we can move on into some details. So the genetic algorithm is fairly simple to explain, so I'll go into it in pretty good detail here. There are two populations, one of phrases and one of measures. The phrases are simply lists of measures of whatever size you want, and the measures are the actual normal definition of the measure. The genome type in our case is this list of numbers. I have an example here. And the mapping from that is very straightforward. You take 0, which is just a rest, 15, which is a sustained previous note or rest, and numbers 1 to 15, which correspond to pitches. And that mapping is very simply an index into a list based on the chord of the current bottom chord progression. So my example here is I have C major 7. And so a 1 is going to map to C, a 3 map to E, etc. You can choose these lists of latitudes to further what your genetic algorithms allow for you. So you construct a population of measures phrases, and then you pass that either to the human for fitness feedback or to the RNN for fitness feedback, depending on which one you're training in, computations, crossover, and repeat. The mutations that are listed here, they're pretty much the same as we see in general. The only difference is we added a bit flip mutation for the RNN only. The theory here being that because the RNN can listen to the samples, what is attacking to be faster than humans, we can use mutations that are unlikely to improve the gene. So whereas with humans, you want to use somewhat musically intelligent mutations, like reversing things, flipping things around, that hopefully preserve the musicality of that measure. The RNN, because it can listen to thousands and thousands and thousands of samples, we can get mutations that are unlikely to improve, but sometimes they'll make an improvement that one of these other mutations could do. Crossover is simple tournament style. There's really nothing innovative in the genetic algorithm here. What we're really interested in is how does the RNN mutate as. So the RNN. I won't go into too much technical details about its architecture. I don't know what the level of familiarity is, but it should suffice to say that it is a fairly standard LSTM recurrent wall network. So that's LSTM just refers to like the architecture of the nodes. It's got 2 layers, 256 nodes per layer, and the only really interesting thing here is the input. So instead of one note as the input at each time step, so you pick some MIDI pitch, passing 50, you get some output, which normally when you're generating music represents the next note. So you have some probability distribution over the list of possible notes. You pick the highest one, that's the next note. But when you're trying to use it as a fitness function, you also want to basically, technically you're doing the negative log likelihood, but basically it just means you check the note that's actually played next and the note that your network follows played next. And if you get it right, it's good. And if this is high fitness, you got it wrong, that's bad, and it's low fitness. And once you pass the whole sequence, you just get this magical number, which represents the fitness. And the input includes the chord as well. So when you train this, you give it the note sequences and the labeled chords. And then when you want to do fitness, you give it your sequence, the labeled chords, and it gives you some fitness level. Okay, so we've heard some examples using the basic architecture. So I'm going to talk about some other kind of qualitative results that we found super interesting. The first two are about the human feedback, because of course the initial motivation for this is that human feedback is bad. So what do we mean by that? This shows the number of times feedback was given to a set of 17 measures. So what we're looking at here is the difference. It's not all uniform. Some measures got a lot of attention from the trainer, some measures got little literally maybe 1 or 2 points of feedback, which means they're essentially getting no information. And so improving them is pretty unlikely. Basically just guessing. The second is the standard deviation of that feedback, also not only inconsistent, but also really high. So like 4.5 standard deviations is tremendous variation. And having this kind of inconsistent feedback is definitely not helping the process. So with the end, we have some different properties that we can. The first is about pitch hierarchy, in which pitches are associated with what chord. So if you imagine playing a chord, playing this one note over and over and over, what is the fitness? And that's how we approximate what the RNA thinks of, just like a single pitch. But you wouldn't want to pass in just one pitch, because as we show later, that's also not a good idea. So you can see that E, G, and D are getting really high fitness if you're playing like a C, 7 chord, which is good. C is getting surprisingly low fitness, which is interesting. Whereas C sharp and F sharp, which normally we consider dissonant, and like probably aren't in the training set of this recurrent neural network very often, given this chord, get low fitness. So here we're just seeing that there's some primitive understanding of which pitches belong to this chord. And we also have a chart of 3 different types of music. So we get random music, so random MIDI, just the time of whatever chord is being labeled, and then some actual real jazz that we got from the one jazz database with labeled chords. And hooray, the actual music is given high fitness. So that's good to see. And this is just a quick note on consistency. So basically don't pass in sequences that are too short, because the fitness consistency will be really bad. So for us, that means you want your phrases, your number of phrases to really add up to like 15 or 20 measures. Otherwise, the fitness feedback is going to be high. Okay, so what have we learned from these experiments? First, that's possible, right? This isn't super surprising, since the founding idea is that if RNN can produce reasonably compelling music, then they should also know what that music sounds like. But it's nice to know that this actually works with reasonably little engineering effort and pretty much minimal, I would say, knowledge. And another lesson learned is that the RNN doesn't technically model creativity in any way. So it's really easy to find sequences that are given good effectiveness, but aren't like no one would ever propose them. They're definitely not from the training set. And there's a lot of interesting work to be done here. As long as interesting work on more work on like the human evaluation and the psychology side of humans as evaluators. Okay, so I don't know how much time I have left, maybe 5 minutes. I'm going to play at least some of this demo and composition, essentially. Titled "Do Not Fear Our Musical Robot Overlords." And the premise of this piece is to kind of show off the evolution and the learning process of the genetic algorithm. So it starts off with very, very bad generation 0 examples. And there's evolution of specific measures. So a measure will be repeated over and over with increasing generations, so you can hear the change. I'll kind of give an annotated walkthrough. So the crappy trumpet synth here represents a sample where the RNN is the fitness function. And you'll also hear a nice sort of sample saxophone, which represents when the human was acting as the fitness function. And all not brass instruments were just composed and added by itself. All right, so the next section, you hear the measure evolution. So every time there's a clap, it's a new generation. course, represents the human trained RNN. And the piano, of course, is just played by itself, kind of as the provide some kind of comparison for what human processing sound like. You can see there's a lot more variation in rhythms, since our genetic algorithm has very little rhythmic variation. And this was RNN training. So this thing here is the later generation of the original thing you heard in the opening section. So you can see some evolution there. These two sections here are actually homages to Albao's performance with Gemdown at X. These are like exact copies of what they played. This is another point comparison to how I performs. And the opening theme again. Thank you. The code is on GitHub. I have some thought-provoking questions. I don't actually let go until when am I done? Oh, perfect.
So questions and comments. As one started before evaluation question, I didn't quite get exactly what you train the argument on.
So we tried to train the RNN. We did successfully train the RNN, but the most successful outputs were used by the models trained by Google. And unfortunately, all we know about the training set is that it's massive and that it doesn't contain any strange, like it's not specifically trained on jazz, it's not specifically trained on some genre of music. It's kind of ambiguously trained on a huge corpus of music. And the main limitation there is you need chord labels for each time step of your input, which is a tremendous effort. And there weren't really any reasonably large data sets that had chords labeled well at every time step.
What you're saying is the RNN was the one trained by Google on a massive set of music scores, and what it gives you, therefore, as a fitness is the level of musicality of the piece.
Yeah, that's kind of the hope, right? Like you trained it on a huge set of several genres. It's kind of a strange approximation to its general musicality. I would love to try this on a specific genre or a specific artist even. If you could amass enough label data to train these networks, because they are not easy to train, then you could get some measure of fitness that corresponds to a specific genre or a specific type of music. But this one is more just general, general music.
It's a very good approach. It would be interesting. With RNN, as with a lot of models in deep learning, you can also specialize the network. So you take the trained version, and then from there on, put some microdis or whatever properties you find out, and then fine-tune the configuration.
Yeah, that's actually probably doable with some serious engineering effort. Wide just database could be made to do that. When we looked at it, the correlations were very inconsistent in terms of format. They almost seemed wrong sometimes. But if you did have a few hundred, even maybe samples of something you could find it.
Questions from the audience? Yes.
Thank you very much for your talk. I appreciate the tilting of the questions. One is a little popular, and another is more detailed. We have a website called Austin Intelligence.
The dangerous claim.
Yeah.
I did not write that.
But what could be this production and the second question is about evaluation and how do you intend to that people have separate teams working with users?
So I want to answer this question, but it's a little hard. So let me start the second. So our human trials in this experiment were very limited. So it was myself and another author on the dream, and the analysis of the feedback was also pretty minimal. We all wanted to prove that human feedback is pretty consistent, which we then loosely assume means that is why human training kind of doesn't get any better after a certain point. You get to about 10 generations. This is the same. You get to a certain point, and it just stops the changes, but it doesn't get any better. And part of that is, I think, the limited phenotype expression or how expressive these are. There's so much more I think we have to learn about the human input and how you give it, especially because that's not given much attention in Gengen, or at least not specifically do that, and given almost nothing in our work. So deciding like how do you best attribute the feedback that you give? Because right now it's just you press G on your keyboard and it goes +1 to the measure that was playing 2 weeks ago because there's some delay, which like we didn't even study the length that it should be, should it be dynamic. The feedback is more than just a +1 or -1 on the kind of thing. So finding a better way to distribute that feedback is definitely. The second question is I think it partially goes back to what I was saying about what you train this IM on, because the only thing that's affecting what you get out is what you are. When it comes down to it, that's all that matters. Either what you choose for your genetic algorithm structure also matters as to what is possible to use. But I think the intelligence in our system really comes down to what you train the IM on. And there's no explicit model for creativity. It means you're limited at some point, right? Like you can train the RNN on more things, but that doesn't mean it will be able to produce a wide variety of specific things. It means it will be able to produce general things. So like, you take a huge Java database and a huge reggae database, you're not going to get some reggae and some jazz. Which maybe is cool. Maybe that's what you want. But there is not as much intelligence there as we know.
Yeah, just a comment on I think what's interesting about that possibility is stuff comes a computational process.
You take your data 4 days later, 4 weeks later, you get it. Yeah, that's true.
But I think the other question also about evaluation. Yes, we can learn more about fitness, but it also becomes an opportunity to learn more about preferences. But given the amount of information you're looking at, you have screens of notes and trying to find examples of specific experimental methodology. So that's absolutely a good way to discuss
very fast. Although, like, we have very often there's so much that can be listened to and you should at least align the range of the feedback to be fair in the same way as the island. That isn't necessarily true because actually numbers. A quick idea that we're so that so first it would be nice if it's in relation to not only computation but computation. We will do as well because it's no longer doing something and the second thing is why not using the human feedback, not directly to the feedback, but to use the human feedback to fine tune as an addition to the selection and operation of the population on the island, or to use the human feedback to fine tune the island eventually. That would be interactive island engineering. I don't know that exists. I don't know that possible. That way this kind of longer. All right, let's take a speaker. Next, we have Liam Good-Acker. He's running some technical problem on part of his computer that nobody does on the projector, so it's different. This mic working? That's the mic. Oh, that's a mic. This mic is working. Great. So as long as I can remember, I wanted to make music on computers. But I always found all the existing platforms that I could find either too restrictive or just too complicated. I'm not that good with computers, and just I never found my voice on them. So naturally, I decided to create my own system with Poly. And what I came up with was a system called Context, which is a modular sequencer for PD. So PD, if anyone's not familiar, pure data, it's a visual programming environment, very similar to Max MSP, also built by Puckett. It's open source. Yeah, so modular sequencer, what does this mean? I'll just give some definitions. First of all, by a sequencer, I mean the context sends messages to other PD objects, abstractions, instruments, basically determining what happens when. So the point is that context doesn't have any audio capabilities other than sampling. It just simply acts as an instructor to other instruments. And modular. By this I mean the context can be replicated and interconnected within a PD patch any number of times. And the result is that you get a network. And by a network here, I mean very visually with a network. You'll see a screenshot in a minute. And so the idea is that the composition that the composer builds is in the form of a network. So there's an old piece of wisdom in computer programming which says that you should build individual tools to solve individual problems. But for better or worse, I took the exact opposite approach. Context is an individual tool, so it's designed to solve as many problems as I possibly can, which was a nightmare in terms of implementation, but I think now that it's done, it's quite powerful. Maybe the subjective word. So what is context? An individual context unit
is a step sequencer, a sample player, an embeddable timeline, a random selector, a storage bank, and in addition, our context has its own language, which is used to control all of its functions and also to build formulas and algorithms for its output. Again, you'll have at least a screenshot of an interactive demonstration in a minute, so hopefully this will become clearer. The aims of context, what I'm aiming for is composers to be able to build their own sequencing environments. By a sequencing environment, I mean basically an alternative to a DAW system or a tracker or something like that. What I want is for context to be able to do everything that a sequencer or any software suite could possibly do. Does that, but that's the intention. And secondly, for the composer to have a great deal of choice when it comes to building that sequencing environment. So the idea is that one user can use context to come up with something that's entirely linear. Another user can come up with something that's entirely nonlinear, stochastic, and so it's extremely adaptable. And finally, another aim is to make context intuitive and simple to use using a GUI. Now, I think that's I doubt it's simple to use at this point, but I'm getting there. So here it is. I'm going to show you a little screenshot. And I'll see if I can play something. This is very low tech. I'm just going to pull this up here and see what happens just so that you can get a data. So it's a very visual system. Which I wish you could see right now. I'll maybe play a little more at the end. I'm going to try my best to describe what I see, and you can come and see it later on at any stage. So each of these units is essentially a timeline unit. It's a very familiar, anybody who's familiar with electronic music production will recognize it. You can see on each of these there's a cursor that will pass left to right on the screen. And the line along the bottom, those little boxes, that's called pattern. That's just a simple step sequencer. So that's just going to play whatever pattern you put into it, and you can use the mouse to select numbers and on and off, things like that. The line up and down the side on the y-axis, that's called the burst. That's maybe less intuitive. The burst toggles all fire simultaneously at the very end of the pattern, so they all come at once. So that's used to multiply signals to make chords. But also, more importantly, you can randomize which toggles are going to fire. So in the, so like this one here, these toggles, I've had it set so that exactly 2 of those will fire, but which ones will fire is going to be random. So that means that you can immediately build Markov chains using context. And it means that the Markov chains, what they're connecting isn't necessarily individual notes, it could be individual notes, but it's basically musical phrases of any length. So the pattern and the burst, I've gone over that. You can see here context works as a sample player. Basically, all of this space, any of these individual units are potentially can hold samples, and they can hold any number of samples, and you can move them just like on a DAW. You can move them and resize them across the screen. It's never going to be. It's a bit clunky, but it does work. So potentially, you could make a whole composition just on one sort of large extended context. Put samples in there, and just like in a regular DAW. But then also you have the ability to connect these together in the network, as I described. A few more functions I'll mention here. This context and this one up here, so the purple and the cream-colored ones, are functioning as selectors. Now, basically, anytime they receive any input, they will fire one of those toggles. So that will sort of continue down the network. You can think of it as a big helter-skelter, basically. That's a big marble one. Sort of information starts at the top and tumbles down in a random way, or a non-random way. And then finally, another thing that's nothing really to look at here, but I mentioned earlier that context sends messages to other PD programs. All those messages, you just type them in, but they're also subject to an interpretation language, which I'm just calling the output language. It lets you build formulas and sort of add random notes in there. So, for instance, you can see, I mean, this is the one example here. You can see this is a little formula in the output language. What that means is whatever note it receives from here, take that and multiply it by 1.5 or by 0.5. So this was a random note up here, and then this is going to multiply that by 0.5. So what the result is, you can have sort of little relative melodies. You have an input note at the top, and then the whole thing filters that. So there's actually a lot more that it could do, but I'm running short of time. What have been my findings with this process? First of all, this might sound a bit ambiguous, but context is very good for composers who don't have a master plan with their composition. That's me, I'm describing myself there. I get very intimidated by the sort of omniscience of a DAW or a tracker where you have to know what everything does before you start to do any one thing. The beauty of working with context is that you start with one little unit and you just make a little pattern, you make it do whatever you want, and then that inspires another idea and you can connect. You create another one, and then you connect them together. And I find this a very intuitive way of making music. And I find it very good because you can change, you can alter things very fast, very easily using context. Two, this is a mouthful. I wish I could make a less dense version of this sentence. Context networks let you represent music in linear, nonlinear, stochastic, structural, algorithmic, and metacreative terms. I'll go through those one by one. Linearity, I think that's apparent. The pattern is just a simple linear sequencer. Nonlinear, anytime you make a connection, you're sort of breaking that linear element, jumping from one context to another. Stochastic, the burst, as I mentioned, has a very powerful random, you have a lot of control over the randomness, if any, in the composition. Structural, the burst can also designate patterns, and you can build complex, multi-layered structures, just visually there on the screen. Algorithmic, you have the output language, which is there to build formulas and create node generation. And finally, metacreative, this is something I haven't mentioned yet. Any function, anything that context can do has a corresponding command on the input language. And what this means is that context can control itself. So the data, I say it sends messages. Usually it's going to be sending musical messages. It can also send meta messages. So one of the messages, one of the toggles that you see could be a message to open or close another toggle or to alter one of the notes. And what this means is that the music can evolve either in a predetermined way or in a random way. So you get some random alterations to the network which propagate over time. So that's each one of those statements. So context lets you represent music in these terms. It also lets you interact with music with a composition like this, because all of these, the linearity, the structurality, basically all it is opening and closing toggles, so you can just do it like that on the screen. And then last section, perhaps the most important part, context offers you a choice about how you incorporate linearity, stochasticity, structure, and algorithms. Basically, all of these that I've described, they're options, they're offered to you, but you're free to choose them. In designing a network, you design exactly how linear it's going to be, how nonlinear it's going to be. You're going to decide. It could be that you have a composition with just one random note in the whole thing. It could be that every note is random, every time event is random. And all of these decisions are determined pretty much visually on the screen. And then the final thing is that the choice that you make there about how your context network is going to function is non-restricted. So it's very easy to have it completely linear in this section, and then it jumps to something completely random in this section. So that's it. I'll just say that finally that my intention I wanted to build something, obviously I said this at the beginning, that I could use. And it's been that for me. I've been composing it for some time, and I'll be demonstrating tomorrow at around 10:30, so you can come and see some of the work that it's capable of doing. But ultimately, my dream is to see other people use this tool in ways that I haven't imagined. So it's there. It's the website. Actually, I think it's contextsequencer.wordpress.com. The code is available. It's beta. There's still some flaws, but it's well documented. And I'm working on it all the time. So,
thank you. We have a few minutes for question. I'll start by saying that for those who didn't know, we are in the evolutionary review session, and that has nothing to do with evolution, and that's because we have a number of consultations this year, mostly people, and that's the problem of the diversity of our community, is people that are more on the artistic side might not have the funding to come with their work is relevant, and in the future years we might try to address that problem. But there was a good preview and opening for the next session that Oli is gonna chair, which is the session on networks, and we have that networks and other networks, and that certainly is a sort of network-oriented system. Yeah. Any questions, comments for Liam?
So how, thinking about the complexity, are the laptop operations, are they kits, or can you do that? How can you do it, like, for me as a composer,
right. Context is pretty good at that. For one thing, let's go back to this screen. For one thing, you can see the time unit in the that just determines the time, that little number box. That's randomizable. There's a setting there, so it can be sort of 1, 3, 5 seconds, and then you can make it so it's 1, 2, 4. So you have some options for making. I made some quite interesting sort of Markov chain rhythms. It's very easy to because of the burst. It's very easy to create tuplets, and you can have polyrhythms quite easily. I'd be happy to show you. It's easier to show than to describe.
More questions, comments?
No, I've been working in a cave for the past 3 years, literally. That's why I've shown it to people. I do have a few people. The thing is that it's at this point it's quite hard to learn how to use it, and that's something I'm very concerned with. I'm planning to make a video tutorial series. There's a manual which describes everything. It's 60 pages long. I don't know whether I want to make it as accessible as possible. As I said, I'm looking for the day when some of the composers should do something that they've done.
It looks a bit like a candidate for a sort of PD-based, live, not to say live coding, but live interface, existing composition, but play that live and everything. And it could be possible to make it with the team of this session to actually evolve context.
I had that very idea as well. I'd love to learn more about how evolutionary algorithms work to see if it's possible.
Any more questions?
have you considered the strong analogy there between this kind of modular and
Right. Yes, in the paper I've drawn that analogy. I mean, that was the initial inspiration. And of course, on a certain level, you can think of, I mean, what happens here is that everything's filtered through here through time, right? So there's just, you get these feedback. Everything works essentially by feedback, but it doesn't spiral out of control because the time is delayed. But, I mean, there's also the analogy there if you think of sort of, this is dealing with very slow events and digital modular synthesizers doing basically the same thing, but just a sample rate instead of.
All right, we are time. Thanks again. So this is time for the first coffee break. Let's go out of the room and see if there is a coffee break there, and then we'll reconvene another programming for a minute over there. I believe it's in 15 or 20 minutes. Let's have a look. Okay. 20 minutes? 30 minutes. Oh, it's a pretty generous coffee break. So yeah, we'll come back here at 10:30, and I'll rally outside anyway.
Oh, that's great.
I'm gonna move this whole room closer.
You're Anna.
Yeah.
Hey, how's it going?
All right.
Nice to meet you.
Good to meet you too.
Yeah. Thanks so much for all the help.
Yeah, it's been my pleasure. I know I only have limited power, but I'm gonna do what I can.
You went far with your power.
We're gonna move everything closer because people can't hear or
I
see.
assume so. Okay.
things.
So that means we need to just stop this broadcast, right?
Yeah.
Yeah.
I
Yeah.